Now that we have all the pieces in place, we'd like to apply the momentum principle to the rocket problem. Recall that the momentum principle is that the external force on the rocket on the system causes the momentum of the system to change. And the fundamental definition of a derivative is to look at the change in momentum between sometimes t plus delta t, our two states that we've identified, divided by delta t. Now recall that we had the momentum of the system at time t was the mass of the rocket times v bar of the rocket at t. I'll just quickly show mass of the rocket, Vr of t. And we had the system at time t plus delta t, where we had delta m fuel equals minus delta m rocket. Here we had mr plus delta m, and we had the velocity in the ground frame, which we saw was equal to, so let's write out the momentum of the system at time t plus delta t. That was a little bit longer. P system at t plus delta t had two pieces. It had mr plus delta mr times v of r of t plus delta t. And we were subtracting. Now, because we made this change, that's minus delta mr u plus v of r of t plus delta t. And this, recall, was the velocity of the fuel. Now we're in position to apply our momentum principle, because we have expressions for the momentum of the system at time t and at time t and at time t plus delta t. So now this will be a big expression. So we'll write external force is the limit as delta t goes to 0. Now here, our first term is m of r plus delta mr times the velocity of the rocket at time t plus delta t. And now we have the fuel term, minus delta mr times u plus v of r of t plus delta t. And we have to subtract from that, and I'll indicate that with a slightly different color, mr v of r of t. And the whole thing we're dividing by delta t. Now, let's look at this expression first, because there's some very nice simplifications. The first thing we can see, let's look at this term delta mr times v of r. Notice we have minus delta mr v of r here. So those two terms cancel. And we're just left with three other terms, and let's write them out. So now we have the limit as delta t goes to 0. And I'm going to combine terms in the following way. mr times v of r of t plus delta t. And over here, I have mr minus v of r, so I have a minus v of r of t divided by delta t. And now I have one more term here, and I'm going to write this as minus the limit as delta t goes to 0 of delta mr over delta t. Remember, this term canceled. We only have the speed of the fuel relative to the rocket. And in both cases, this is our first term, and here's our second term. Let's look at these limits. Notice in here, we're just taking v of r of t plus delta t minus v of r of t divided by delta t, and that's precisely the definition of the derivative of the velocity of the rocket. So this first term, our expression, becomes the external force is equal to the mass of our system times v of r, the velocity, the derivative of the velocity of the rocket. And the second term, this is the rate that the fuel is changing in the rocket. This is rather the rate that the mass of the rocket is changing. So that's the derivative dmr dt times the relative velocity of the fuel with respect to the rocket. So This equation here, I'll box it off, is called the rocket equation, which we've derived from the momentum principle using our momentum diagrams. And you can see that this is what people refer to as rocket science. We would now like to look at some applications of the rocket equation, in which we have an external force plus dmr dt, where mr is the mass of the rocket at time t, times the relative velocity of the exhaust velocity, was equal to m of r dv rocket dt. And now we want to consider some special cases. So our first example will be a case when there's no external force. Now, this might be characteristic of a rocket that's far away from any type of gravitational interaction and is either speeding up or slowing down. This is a special case that will enable us to understand our problem. Now, let's consider, we'll draw a picture at time t, just to remind ourselves. So we have mass of the rocket. It's moving with the velocity v of r of t. And we're going to call this our plus I hat direction. And then at time t plus delta t, we have our fuel, delta m fuel, which was equal to minus delta m rocket, moving with a relative velocity u plus v of r of t plus delta t. And our rocket itself is moving with v of r of t plus delta t. So in our coordinate system, we have to remember that the exhaust speed is relative to the rocket. And we define that to be u. Since its rocket is moving forward, and we've chosen plus I hat in that direction, it's minus u I hat. And we can write our vectors Vr as v of r I hat. So our rocket equation in this special case becomes dmr dt minus u I hat equals mr dvr dt I hat. Now, in this equation, remember that it's important to recall that m of r is a function of time. And unless we have an explicit model for how the mass is ejected, in principle, we can't solve for the time behavior, but we can look at this differential equation just by eliminating the time completely by multiplying through by dt, in which case we have minus dmr u equals m of r dvr. Now this is separable, and I can integrate it, so I'll bring the terms minus dmr over mr on this side times u, and that's equal to dvr on that side. Now, when we integrate, we're going to be integrating mass of the rocket, say at some initial time, t initial, to mass of the rocket at some final time. And over here, we're going to be integrating the velocity from some initial time to some final time. And both these integrals are straightforward. On the left-hand side, we have a natural log, so we have minus u, natural log of mr t final over mr t initial. And this side, we just have the velocity difference, v of r at t final minus vr at t initial. Now, again, we always check our minus signs, but recall the mass of the rocket is decreasing. So the log of a fraction is negative, so we have a positive quantity on this side, and that's indicating that the velocity has increased on that side. And so we conclude that the velocity of the rocket at its final time is equal to the velocity of the rocket at its initial time. Now here, I'll keep this minus sign in here, minus natural log of mr t final over mr t initial. Now, in our answer, we need to know what the mass of the rocket is at the final time. So in general, this equation is still not going to give us an explicit expression for v at t final unless we have one special case in which our final time is when all the fuel has been burned. And our initial time is the rocket with all the fuel there. And then this ratio is a known ratio. And you can look at a variety of different examples for that. So there's an example of solving the motion of a rocket with no external forces. We've seen the rocket equation, and we've studied the example when there's no external forces. Now let's consider an example when the external force is not 0. Well, one of our examples is just a rocket taking off in a gravitational field. And so when we want to focus on the external forces, let's draw our rocket at time t. And now consider what are the force diagrams on this rocket. Well, we have a gravitational force, mg. So we're going to choose j hat up. So now what does our rocket equation look like? We wrote the exhaust velocity as minus mu j hat. And so if we write this now as a vector equation in the j hat component, we get minus mg. We have the rate that the rocket mass is changing. And this is in our, remember, dm dr dt is going to be negative. So there's a minus. And over here we have another. This is u, because u is minus u. And finally, we have m rocket dv r dt. Now, once again, we're going to try to integrate. This is actually equal. And we're going to try to integrate this equation to find a solution for the velocity as a function of time when all the fuel is burned. So what we do is we'll multiply through by dt. And we have minus dmr times u equals mr dvr. And this is mass of the rocket. And now let's divide through by mass of the rocket. So we have minus g dt minus dmr over mr u equals dvr. And once again, we can integrate this equation from some initial time to some final time. I'll just denote that by I initial and I final. And what we see here is we have minus g times t final minus t initial because we're integrating with respect to time. Here we're integrating mass, so that's minus mu, natural log. And I'm going to write this as mr final over mr initial. And over here we have vr final minus vr initial. And let's just remove that time t. And so now here is our rocket equation. Now what we notice here is, let's look at some rocket taking off. So suppose that at t initial equals 0, we have the special condition that vr initial equals 0. And mr initial equals the mass of the rocket, dry mass, that's all, that's not counting the fuel, plus the total mass of the fuel. And the final, at t final, when the engine turns off, we're going to try to find this velocity at t final. And our condition for the final mass is all the fuel's been burned, so this is just the dry mass of the rocket. And so what we get is we get minus g t final. Now I'm going to switch the sign here. So we have, if I invert the log, that will give a minus sign. And I have plus u log of mr of d plus mass of the fuel, that's the initial mass of the rocket, divided by just the dry mass, and that's equal to vr at t final. So one of the interesting questions that you might ask is, how fast should you burn the fuel? And what will that have to do with the final speed? So we can see from this expression that if you burn the fuel for a very long period of time, so T final is big, then this piece will diminish the final velocity. So if you want the fastest speed after you've burned the fuel, you want to burn the fuel so that T final is as short as possible. We have the shortest burn time will give us the largest velocity when all the fuel has been burned.